Mr. Newitt is back.
And Mrs. Newitt.
We're having a great time here. We're doing Chapter 3 now, Vector Components. And we know an initial velocity here of 50 meters per second, and it is occurring at a 20-degree angle with respect to the horizontal. And so we're asked to find the horizontal and vertical components of this vector. So let's start with the horizontal here. We want to essentially figure out what the v sub x, the x component of this velocity is, given that it's at 20 degrees. All right. So we have a right triangle that will be formed here. This will be our velocity in the x direction, and then we will also have a velocity in the y. So we'll label this v sub y and v sub x. Okay? To find the v sub x, we will be using the cosine function because cosine of an angle is the adjacent side over the hypotenuse. And for our 20-degree angle that is right here, the adjacent side would be our v sub x side. So to find the velocity here, we'll take cosine 20 degrees, and that is going to equal the velocity in the x direction divided by the 50 meters per second that we have as our hypotenuse. Doing some quick calculation there, you should get a value for your velocity in the x direction of 47 meters per second.
Okay, that means we're left with finding the v sub y, or the vertical velocity, and we'll use trig functions again. This time, if our 20-degree angle is here, we are looking at the opposite, and we know that for the opposite side, we would use the sine function. So sine of the angle is opposite over hypotenuse, and so in this case, we could say the sine of 20 degrees is equal to v sub y, which is our opposite side here, divided by our hypotenuse, which is 50 meters per second. And if we calculate that out, that leaves us with our v sub y of approximately 17 meters per second. So overall, if we take a look at our triangle here then, we have a horizontal velocity of 47 meters per second and a vertical velocity of 17.
Mr. Newitt is back.
And Mrs. Newitt. Today we're going to take a look at resultant vectors. We have a situation where a biker travels 4 miles east and then 2.5 miles north. What is the resultant displacement? First thing we want to do is set this up as a vector diagram. 4 miles east would be represented by an arrow to the right, and then 2.5 miles north would be an arrow upwards. Notice that when you draw out a diagram, you want to do a couple of things. First of all, be sure to put the arrows there to show direction. Second of all, draw them head to tail. So after I drew the 4-mile arrow, right here at the end of that arrow is where we start the next one. And then lastly, try and make your arrows at least somewhat to scale. That way when we draw in our resultant, which begins here at the beginning of the 4 miles, and ends over here at the end of the 2.5 miles, we can see a pretty accurate description of what that route was.
So the next step is finding the resultant displacement. This will involve us finding two things about the resultant. One is its distance, and the second is the angle that it occurred at. let's start with the distance. We have a right triangle now that has been formed as a result of this. And so to find the length of the resultant here, it's simply a matter of using the Pythagorean theorem. We know the two legs of the right triangle are 4 and 2.5, so I can take 4 squared plus 2.5 squared, and I know that has to equal my resultant squared. And so then doing the math for that, the answer I will end up getting for my resultant is 4.7 miles.
Okay, it's kind of tempting to stop there, but remember that when they talk about displacement is a vector. A vector is not complete unless they include the angle. So even though nowhere in the problem does it specifically say give the angle, they expect that your final answer will include the angle of this displacement. So here's the angle that we're looking for. That's our unknown. We have a number of different trig functions that we could use to find it. Probably the easiest is to go back to our original numbers of 2.5 and 4, because those are the two right sides. They would be related by the tangent. So the tangent of our angle is going to be equal to the opposite side over the adjacent side. And in this case, that would be 2.5 over 4, and if we do the algebra, we end up with an angle of 32 degrees. Future Sioux Falls physics teachers looking at a practice problem on resultant vectors. Here we have two vectors. Notice that these two vectors are representing velocities. So a vector could be a velocity, could be a displacement, could be a variety of things, but these are velocities. 12 meters per second along the y-axis and 32 meters per second at 20 degrees above the x-axis. So the first thing that we're going to want to do here is sketch out a little diagram, and it doesn't necessarily need to be perfectly to scale at this point, but enough to show us what general direction we're going to be looking at. We'll start with this vector here, 32 meters per second at 20 degrees above the positive x-axis. That would be off in this quadrant here. So we have 32 meters per second with an angle of 20 degrees. Our other vector is 12 meters per second along the positive x-axis. Now again, to really see what our resultant is going to look like, we need to draw these head to tail. So we have our initial vector drawn. Head to tail means that we go to the point where that vector ends and use that as our starting point for our next vector, which is on the positive y-axis. Positive y-axis is straight up. Notice that that arrow should be a fair amount smaller than our original arrow because we're comparing 12 meters per second to 32. So here is our second vector. And now we can begin to see graphically then where our resultant is. Our resultant starts at the same starting point that we used for our initial vector and ends at the ending point for our second vector. So we can kind of see, generally speaking, where this vector is going to go. Now we need to start doing some calculations to see exactly what its value is going to be. Notice that our first vector, the 12 meters per second, is pretty simple to work with. It's in the straight vertical direction, so it doesn't have any horizontal component at all. It just has a vertical component in the upwards direction of 12 meters per second. Our second one, though, the 32 meters per second, is really taking us in both directions. It's traveling to the right along the positive x-axis, so that would be in the x direction, and it is traveling upwards So that would be in the y direction. Before we can begin to combine the two vectors together, we need to know what these individual amounts are. So we have our angle of 20 degrees. We'll start with the x component, and the x component would be the cosine or the adjacent side. So the cosine of 20 degrees is equal to the adjacent side over the hypotenuse, which is 32 meters per second, and that gives us an x component of 30.1 meters per second. We can repeat the same thing for the vertical component, except that the vertical component is opposite. So opposite would be using the sine, and that would be our vertical velocity divided by our hypotenuse of 32, and that gives us a vertical component then of 10.9 meters per second. Now, basically what we have is we have three components to deal with. We have one component in the horizontal direction, and then we have two components, the vertical component of our vector at an angle and the vertical component of the vector that is heading straight up. Those two together will provide the vertical component for our resultant. So now we can kind of draw a more detailed diagram of what the resultant's going to look like. So as we draw our resultant, and again remember that over here on our initial diagram, we have kind of a general picture of what it's going to look like. We know it's traveling to the right and it's traveling up. The horizontal component for that will simply be 30.1 meters per second, because that's the horizontal component of our 32 meters per second, and our other vector doesn't have any horizontal component at all. Then we want to add the vertical components. We have the vertical component from that 32 meters per second. We just calculated the vertical part of that as being 10.9. And then we also have the vertical part that is added in from our other vector, and that vertical component, and we can say that that's vertical component 2, would be 12 meters per second. So now we get into the math part of it. These two together would be adding to give us a vertical component overall of 22.9 meters per second. So that is our vertical component of the resultant. Now we finally are ready to calculate that resultant velocity. We have a horizontal component and a vertical component, which means we can go back to the Pythagorean theorem, take our two values that we have in the x direction, that's 30.1. In the y direction, that's the sum of our two parts together, that's 22.9. And doing the Pythagorean theorem, we get a resultant value of 37.8 meters per second. Now, one thing to keep in mind is that unfortunately we are not quite done here, because we also need to include the angle. Anytime you're dealing with a vector, your answer is not complete without an angle. And in this case, probably the easiest is to go back to tangent. Tangent is equal to opposite over adjacent. Our opposite side was 22.9. Our adjacent side is 30.1. And solving for the angle, we get an answer of 37 degrees, and that is above the positive x-axis. Hey everyone, here's your Sioux Falls physics teachers back to look at a resultant vector problem. We have two vectors that are given, and we are to determine the resultant between them. So notice there's going to be a lot of steps involved in this problem. It's actually not that difficult to do each of the individual steps. You just need to realize going in that it does take a while. So we're going to have quite a few different steps here, but just try and follow them individually. Okay, the first thing we want to do is draw a diagram to kind of show how these are going to set up. 25 meters is at 30 degrees above the positive x-axis. So our 30-degree angle is here, and this arrow then represents our 25 meters. The 40 meters is at 70 degrees above the negative x-axis. So here's our 70 degrees, and our 40 meters arrow is over here. Now, in order to put these together, we need to put them together head to tail. Notice it wouldn't really matter what order, but since we already have our 25 meters over here in the first quadrant, we'll probably leave it there. Head to tail means that we would take this second vector and put it head to tail with the first. Now we can see that our resultant is going to start here at the beginning, and it's going to end at the end of our second vector, and so our resultant is the green arrow. That kind of gives us an idea of what we're shooting for. Now we're ready to do the math. Here's where we need to take our two initial vectors, okay, so our 25 meters, and break them down into their parts. Okay, because if we want to be able to add them together, I don't want to think about this as 25 meters at an angle. Instead, I want to think about it as terms of positive x amounts and positive y amounts. For our second vector, if I think about this being the starting point, I want to break it down into an arrow to the left and an arrow to the right. Okay, now we've done a little bit of math over here. This is going to be your first set of steps to do the mathematical calculations for the resultant. Notice that we took each one of these vectors then and divided them up into their x and y components. So starting here with the 25 meters, we use the sine and the cosine of 30 degrees to figure out an x amount of 22 and a y amount of 12.5. For our second vector, we use the 70-degree angle and the 40-meter amount to find our x and y components. Notice that because the x component is pointed to the left, we have this written as a negative 13.7 meters, and then the positive amount for the y because it's still upwards. Now we've put varying amounts of significant figures on our answers up here. When you're calculating these out, you probably want to leave as many sig figs in your calculator as possible until you get to the very end.
Okay, now that we've calculated the x and y components for the two initial vectors that were given to us, we now can use those to help us find the resultant. The green arrow that we've left here is the resultant vector, and so to find the x and y components of this, we are going to simply add together the x's and y's that we've calculated so far. Keeping in mind we must keep the signs with the numbers. So for the x component there, we have 22 meters. So the x of our resultant will equal 22 plus the negative 13.7. And the result of that is going to be equal to, this is the x resultant of, so we'll have an x resultant then of 8 meters. Then we'll do the same thing for the y resultant, adding those two figures together, 12.5, 37.6, and the y resultant then is 50. So we have 8 and 50.
Once we now have these amounts for our resultant, we have the x amount of 8, the y amount of 50, now we're ready to actually find the magnitude of the resultant itself. At this point we'd use the Pythagorean theorem, x squared plus y squared, and in this case we have 8 meters and 50 meters. And if we look at that and we take the square root, we end up with an amount of 51 meters for our resultant. Now again, tempting to stop there, but that is not the end of this problem. If it says determine the resultant, your answer is not complete unless you have this angle. So now we're back to using the tangent of the angle, which is the opposite over adjacent. And in this case, we have 50 meters as our opposite side, 8 meters as our adjacent side, and so that means our angle is 81 degrees. So our final answer in this case would be 51 meters at 81 degrees.